Hi again. Welcome back. And this series of lectures will be on the kidneys, part 2, on fluid, electrolyte, and pH balance. So the first slide is looking at its review of the major fluid compartments of the body. So we've already been through this once before, but I thought it would be helpful to just take a look at it again. So these are the major fluid compartments of the body. And there are 3 of them, the tan box, the purple box, and the red. And the intracellular fluid is the fluid inside cells. So this is our ICF. The numbers on the diagram I'm not particularly concerned with. I won't ask you for them, but it's percentage of body weight. So, it's just saying that over 60% of your body's weight is due to water. But those percentages I'm not interested in. The extracellular fluid and the intracellular fluid, so the compartments, over half is in the intracellular fluid. So most of the fluid in the bodies is inside cells. That's worth remembering. That portion of the fluid which is outside the cells is the extracellular fluid, which is the ECF, which includes both the interstitial fluid, that fluid between the cells, and the plasma. And there's more fluid in the interstitial space than in the plasma, but again, that's not as important. What you will encounter occasionally is a talk of fluid shift. And it's usually shifting of fluid from either the plasma into the interstitial spaces, which would cause swelling, edema. That's what would bring a person into the clinic. That's what would be of significance. And fluid can also shift the other way, into the blood. So when we're talking about fluid shifting, we're talking about movement, sort of net movement between compartments. And I put a note over here to think about the total blood volume with a question mark. So here the plasma volume is about 3 liters. So is that saying that there are 3 liters of blood about in the body? Well, no, it's more than that. So to go back and review again, remember when we did our hematocrit early on in the quarter? We took a tube and filled it with blood. Let's say it's 100 mils just to keep things simple. And then we spun it in a centrifuge. And afterwards, the blood separated out. And we had packed red blood cells, which was our hematocrit. You remember a typical value, sort of ballparking? It's expressed as a percentage of the total volume. So it was typically about, let's say 45%-ish. Another question for review, do men and women have the same hematocrit? If not, who has a higher hematocrit and who has a lower? At any rate, back to the picture at hand, this is the plasma. And so if the hematocrit is 45% of the total volume, this would have to be about 55%. And that's what's shown in the figure. So, that's enough of that slide. Not a lot to fret over. So, the next slide. By the way, much of what we're doing in this part 2 of the kidneys we've already touched upon. So, in some ways, it's a review of some concepts. So this slide I put together to show the idea of relative concentrations in these major fluid compartments. So identify the major fluid compartments again. Well, there's the plasma, and here's the interstitial fluid between the tissues. So the interstitial fluid again is out here. All that is the ISF. And then we had the intracellular fluid. So there are the big three again. And what I wanted to show in this slide are the relative concentrations of different things in these three fluid compartments. Well, for this to start, let's look at the plasma and the interstitial fluid. And what I put in the box was that all of the small stuff that can fit through the pores in the capillaries goes to equilibrium, more or less. So all the small stuff, with the notable exception of proteins. And proteins are not small, they're quite large. So they tend to stay in the blood. And as soon as I get done writing large proteins, I'll ask you for some examples. That's an L. So, this is review, right? So, give me some examples of large proteins in the blood. Things like the albumins. What else can you name? Clotting proteins. Can you name several specific clotting proteins? Fibrinogen, prothrombin, etc. So I'll say give examples of those. Any other major classes of proteins that you can think of that are in the blood? There are the immunoglobulins, the antibodies. Oops, globulins. And there are lots of others, but just to review. Okay, so that all stays in the plasma, in the blood vessels normally, because it's too large to leak out through these holes. But all the small stuff can leak out, such as sodium, potassium, other ions, all that you can list. Amino acids are small. Glucose is small. Hydrogen ions fit in there. So all of that just goes back and forth. So the concentration in the blood is essentially the concentration in the interstitial fluid. And stuff just goes down a gradient. And since there's no real barrier to diffusion at the capillary for the small things, They just go back and forth to equilibrium. Remember that in the cells, on the other hand, they have the membrane around them that is semi-permeable. So there are little transporters that are on the membranes. So the little cylinders that I drew are transporters. And we looked at, or you have looked at in other classes, several different transporter proteins. We looked at some in this class also. Okay. One other thing to point out for you to perhaps review is the cytoplasm versus the cytosol. You should be pretty clear on the difference between those two. They're both inside the cell, but they're slightly different. So in the next slide, we're going to be talking about the cytosol. So be clear on the distinction, how you would define the difference between cytosol versus cytoplasm. If you have questions, please ask. So the next slide, let's just make a little table for relative concentrations of these different ions. This you should memorize, but the good news is that it's not hard. So let's start with potassium. And so I lumped plasma and ISF in the same group because we just reviewed on the previous slide that they go to equilibrium. So let me back up just a second to the previous slide. This is what we're talking about. These two. Well, actually the plasma and the ISF. Since they go to equilibrium. Okay, so potassium is high. Now these are relative concentrations. I'm not going to ask you for specific units of measure, but relatively speaking, we can just use arrows. So potassium is high in the cytosol. That's where most of the potassium is inside the cells. And there's very little of it in the plasma, in the interstitial fluid. Okay. All of the rest of the ions have a higher concentration in the plasma and the interstitial fluid. Sodium is higher outside the cell, as is chloride, as is calcium, bicarbonate. Those are the big ones. So if they're higher inside the cell, then they're going to be lower on the outside, or excuse me, lower inside the cell. Again, we're just dealing with relative concentrations. So really, all you have to memorize is that most of the potassium is inside the cell. If you have that, then you should be able to figure out the rest of them. If it's high inside the cell, potassium is then low outside. Everything else is reversed. But you should be familiar with that table and be able to answer those kinds of basic questions. Next slide is another review, since we're sort of wrapping up on the chapters on the kidneys. I threw this back in again just to remind you of this idea that the kidneys can conserve but they can't replace anything. All they can do is regulate the loss. But if you're low on fluid, if the fluid drops, the only way to get that fluid back is to drink it. And if you can't drink it, then you have to get an IV or some other means of pushing the fluid into the body. And as long as the blood volume, the fluid volume, remains above a certain level, then we filter it. The kidneys stay open. And we filter through the nephrons, and then we return most of that fluid. Remember the GFR? Remember about what it was? About 180 liters per day flowing through the handle of this mug. And about 99% of it was reabsorbed. And about 1 to 1.5 liters a day of urine was lost. So most of it's reabsorbed back into the mug on the drawing. And we have talked about how GFR can be regulated. Do you remember a couple of intrinsic mechanisms? So let's say review just the idea so you know what we're talking about. 2 intrinsic mechanisms. And then we had 2 extrinsic mechanisms. Intrinsic versus extrinsic, meaning is this mechanism within the kidney itself or is it coming from outside? Ditto marks for mechanisms. So again, you probably should review those. And even you have questions, I expect you to ask. Okay, next slide. Is on osmolarity. So this also is review. This probably takes you back to Biology 160. So osmolarity is a measure of the solute concentration. So I drew 2 beakers, one on the left, one on the right. The one on the left obviously has more fluid in it. The one on the right obviously has less fluid. And I put 20 little dots, 20 little solute molecules in each. And you can count them up. There should be 20 in each. And so the number of solutes is the same, but the osmolarity is different because it's a concentration. So on the left, there's more water, clearly. It's higher in the beaker. So the solutes are more dilute. We still have 20 solutes in each, but there's more water, so they're more dilute, and this has a lower osmolarity, lower concentration. Of solutes per volume. Okay. And on the right, the solutes are more concentrated. So this has a higher osmolarity. And here the solutes are more concentrated. So, any thoughts on what could cause your blood to gain in osmolarity? What could be happening? What about if we had blood loss, hemorrhaging? Would that, just by itself, would that change the osmolarity? Like we lost a liter of blood, a significant amount. That would be equivalent to taking off, this much, let's say. Would that the question is, would that change the osmolarity? It would clearly change the volume, but the concentration would still be the same. In this picture on the right, we haven't lost any of the solutes like we would have on the left. All we've lost is the water, so they have become more concentrated. Things like dehydration. Is most of the time what we're talking about. And dehydration can come from either loss of fluid by sweating on a hot day, or it may just come from an elderly person not remembering to drink. They don't have the urge to drink, and they become dehydrated. It's rather common. So the bottom portion of the figure is the review of this idea of tonic and tonicity, if you will. So tonic is referring to the solutes. So more solutes, more tonic. More solutes, hypertonic on the right. Oops, where do I go here? Hang on a second. Playing with my pen here. Forgot what I was going to highlight. Oh well. Hyper and tonic, more solutes per volume. And on the left, it's hypotonic, fewer solutes per volume. Which way does water flow? Water always flows to the hypertonic, where there is less water, where the osmolarity is higher. Okay, the last slide for this it leads us into the next lecture on dehydration and antidiuretic hormone, where we'll be talking about osmoreceptors briefly. So osmolarity, what we were just talking about, affects the cell size and shape. And cells will either shrink or they will swell, depending upon the concentration of difference of water inside the cell or outside the cell. So, as we've done before, osmosis, a definition of it is that water flows across a membrane, which is a semi-permeable membrane, from where there's more water to where there's less water, down a gradient. So you have to sort of think hypertonic versus hypotonic. Which way does water flow? Flows toward one or the other? It flows toward the higher solute concentration, which is also the lower water concentration. So water always flows toward the hypertonic solution. Okay. More solutes, higher osmolarity. That's what we did in the previous slide. more solutes, higher osmolarity, lower water concentration, and we just talked about how water follows solutes. Water follows sodium. Okay, that's it for this. We'll come back and do, I think, 4 more slides for the next lecture. See you soon.